Hot Jupiters are a class of gas giant exoplanets that are inferred to be physically similar to Jupiter but that have very short orbital periods. The close proximity to their stars and high surface atmosphere temperatures resulted in the moniker Hot Jupiters. Hot Jupiters are the easiest extrasolar planets to detect via the radial velocity method, because the oscillations they induce in their parent star's motion are relatively large and rapid, compared to those of other known types of planets. One of the best-known hot Jupiters is 51 Pegas Cb. Discovered in 1995. It was the first extrasolar planet found orbiting a Sun-like star. 51 Pegas Cb has an orbital period of about 4 days. Though there is diversity among hot Jupiters, they do share some common properties. There are two general schools of thought regarding the origin of hot Jupiters: formation at a distance followed by inward migration, and in situ formation at the distances at which they are currently observed. The prevalent view is formation via orbital migration. In the migration hypothesis, a hot Jupiter forms beyond the frost line, from rock, ice, and gases via the core accretion method of planetary formation. The planet then migrates inwards to the star where it eventually forms a stable orbit. The planet may have migrated inward smoothly via type 2 orbital migration, or it may have migrated more suddenly due to gravitational scattering onto eccentric orbits during an encounter with another massive planet, followed by the circularization and shrinking of the orbits due to tidal interactions with the star. A hot Jupiter's orbit could also have been altered via the Kozai mechanism, causing an exchange of inclination for eccentricity resulting in a high eccentricity low perihelion orbit, in combination with tidal friction. This requires a massive body, another planet or a stellar companion, on a more distant and inclined orbit. Approximately 50% of hot Jupiters have distant Jupiter mass or larger companions, which can leave the hot Jupiter with an orbit inclined relative to the star's rotation. The Type 2 migration happens during the solar nebular phase, i.e. when gas is still present. Energetic stellar photons and strong stellar winds at this time remove most of the remaining nebula. Migration via the other mechanism can happen after the loss of the gas disk, instead of being gas giants that migrated inward. In an alternate hypothesis, the cause of the hot Jupiters began as more common super-Earths which accreted their gas envelopes at their current locations, becoming gas giants in situ. The super-Earths providing the cause in this hypothesis could have formed either in situ or at greater distances and have undergone migration before acquiring their gas envelopes. Since super-Earths are often found with companions, the hot Jupiters formed in situ could also be expected to have companions. The increase of the mass of the locally growing hot Jupiter has a number of possible effects on neighboring planets. If the hot Jupiter maintains an eccentricity greater than 0.01, sweeping secular resonances can increase the eccentricity of a companion planet, causing it to collide with the hot Jupiter. The core of the hot Jupiter in this case would be unusually large. If the hot Jupiter's eccentricity remains small, the sweeping secular resonances could also tilt the orbit of the companion. Traditionally, the in situ mode of conglomeration has been disfavored because the assembly of massive cores, which is necessary for the formation of hot Jupiters, requires surface densities of solids approximately equals 104 grams per square centimeter, or larger. Recent surveys, however, have found that the inner regions of planetary systems are frequently occupied by super-Earth type planets. If these super-Earths formed at greater distances and migrated closer, the formation of in situ hot Jupiters is not entirely in situ. If the atmosphere of a hot Jupiter is stripped away via hydrodynamic escape, its core may become a Chonian planet. The amount of gas removed from the outermost layers depends on the planet's size, the gases forming the envelope, the orbital distance from the star, and the star's luminosity. In a typical system, a gas giant orbiting at 0.020 around its parent star loses 5 to 7% of its mass during its lifetime. But orbiting closer than 0.015 astronomical units can mean evaporation of a substantially larger fraction of the Planet's mass. No such objects have been found yet and they are still hypothetical. Simulations have shown that the migration of a Jupiter-sized planet through the inner protoplanetary disk is not as destructive as expected. More than 60% of the solid disk materials in that region are scattered outward, including planetesimals and protoplanets, allowing the planet-forming disk to reform in the gas giant's wake. In the simulation, planets up to 2 Earth masses were able to form in the habitable zone after the hot Jupiter passed through and its orbit stabilized at 0.10. Due to the mixing of in